So welcome to the first Meow video seminar of the autumn semester of 2022. Today we have the pleasure of hearing Ilario Bonacina speak about vanishing sums of roots of unity in polynomial calculus and sums of squares. Please, Ilario, over to you.
Thank you, Jakob, for the opportunity to talk in this seminar. And so I'm going, so it's a proof complexity talk. And this is based on a joint work with Nicola Galesi and Massimo Lauria. So I will be trying to not assume much from proof complexity, but feel free to stop me at any point. Of course, in the second part, no, in the second part, I guess the people more interested or already focus on proof complexity might enjoy it more. I don't know. Okay, so just a very brief intro. What is the type of questions we're interested about? So we are interested in when you are given a set of polynomials that you might want to use it as encode some combinatorial problem or some constraint satisfaction problem, and using polynomials over some field, using some variables. So that type of question that we're interested in is if this set of polynomials is satisfiable, or from the proof complexity point of view, if this set is not satisfiable, there is no common root, how hard is to prove this fact in some formal system. And during this talk, I will use this somehow color code, like green will be all general definition, orange results, and blue examples. And I tried to put a lot of examples to clarify things. Okay, so let's start with an example. So now you suppose that you have a graph and you want to see if it is tricolorable or not. So one way will be to use, say, variables encoding this very basic fact. If a vertex gets a color, vertex B gets the color C. And there are two possible ways of doing, like using a Boolean encoding, like you have variables, 0, 1 variables, and the variable says yes or no, you get the color. Or you can have a multi-valued encoding where you have variables telling you directly the color of the vertex. And then in the first case, for instance, you could encode your problem of asking if the graph is tricolorable as the problem of finding a common solution of this set of polynomial equations. So the first equation is saying, okay, you only assign a color to each vertex. The color are 0, 1, and 2. The variables are Boolean. And for every edge, you cannot assign the color 0 to both of them, or the color 1 or the color 2. Or you can use in a multi-valued encoding, like now the colors, in this example, they are the roots of unity. So you have 1 zeta, zeta squared. And now the property of not having the same color for two vertices that are on an edge is this polynomial. But of course, you could have chosen a different encoding, like now you have variable taking values 0, 1, and 2. So you could have the analog of this type of polynomials will be, I don't know, zv for 0, zv minus 1, zv minus 2 equals 0. And here you will have a something analog to this type of polynomials, saying, I don't know, zv, zw must be 0, zv minus 1, zw minus 1 equals 0, something like that. But we are interested in this encoding where we use the roots of unity. So they form two natural somehow settings. So these are Fourier variables where you use the roots of unity, or the more common setting where you have Boolean variables. And
Ilario, just a quick question on your previous slide.
Yeah.
So this second condition that the colors are not the same, is there like a systematic way why you wrote this expression, or is it like trial and error, or it is something?
Right. So this is the, so as a polynomial expression, this is zw cube minus zw cube divided by zv minus zw. So whenever you have this top part, you can always expand it as zv minus zw times some polynomial, and then you divide by this thing. So morally speaking, So if you have k colors, then instead of 3, you have k. And this will be, you know, when you divide by this polynomial, when you have this polynomial and you forbid to take the same value, you will get some polynomial of this form.
Thank you.
Okay, so right. So why these two encodings and not the other encodings? Of course, one could choose the encoding that one prefers, but these two have a very nice property that they give rise to binomial ideals, which means that when you consider your polynomials, you only like in Boolean variables, you only need to consider multi-valued polynomial because x squared is equal x. So whenever you have a variable raised to some power bigger than 1, that's the same. And here in the Fourier variable, it's the same. If you have a monomial that takes some variable that has a degree larger than k, you can somehow push it down to have degree at most k minus 1, without increasing the number of monomials in your representation of the polynomial. And one can pass from one representation to the other, expressing using Boolean variable indicator variables, saying which is the root of unity that we are selecting. So z will be a variable taking value in the root of unity, x0, x1 will be indicator variable, and z to some power will be the roots of unity. So one could pass from one encoding in the Fourier variables to one encoding in the Boolean variables. But finding satisfiability or properties like this might be different if you are in one encoding or the other. More questions on the encoding? Okay, so some quick background on before going into the semi-algebraic proof systems. So basically, one reason people study this semi-algebraic proof system is because they are useful to study limitation of algorithms to compute Grobner basis in the context of algebraic reasoning, like Buchberger algorithm, F4, F5, or in the context of sum of squares. They are useful to give limitations of hierarchy of relaxations in semi-definite programming. And the goal of this work, or somehow this line of research, is like to start or push the theory of algebraic proof system, but in the context of Fourier variables, which is not so studied. And the practical motivation is that algorithm to compute like k-coloring or verification of arithmetic multiplier circuits, there are some that are based on Grobner basis computations over the Fourier variables. So it would be nice to give limitation of those algorithms in the context that they are used in practice, not with Boolean variables, but over Fourier variables. Okay, so this is more or less the part on Boolean encodings and some motivation. And now I want to somehow recall, I guess, because, well, I don't know exactly how much proof complexity the people in the audience know, but okay, so it's some part of algebraic proof systems. And I will start with polynomial calculus over the complex numbers. So again, we have some set of variables, some set of polynomial equations, and now the polynomials start with complex coefficients. And now we want to show the unsatisfiability of this set of equations, deriving the trivial equality 1 equals 0 using the following inference rule. You can multiply a polynomial that you already inferred somehow by any polynomial, and sum two polynomials. And now the complexity measures are the degree or the size. And using this rule, if the set of initial polynomial was unsatisfiable, you are able to infer the 1 equals 0. The degree is the maximum degree of a polynomial that appears in a proof, and the size is the number of monomials. Just a trivial example, like suppose that you have this set of polynomials, Boolean variables, and now you say the sum of the variables is 3. This is obviously not possible. So one way to refute it would be take this polynomial, which is x plus y minus 3, and multiply it by x minus y. Right. So this would be x squared minus y squared minus 3 x minus y. since x squared and y squared are equal x, this will be, well, I guess, yeah, minus 2x minus y. And this is intended to be 0. So this means that you have inferred that x minus y is equal 0. And now you're summing these, you get 2x is equal 3. And now taking squares, you get 2x squared is equal to 3x, which means x must be 0. And now you similarly you get by similar thing you get y must also be 0, and then oops, and then summing again here we get 0 equal 3 or something like that, which after dividing by 3 you get 0 equal 1. So by some very trivial multiplication and summing you get 0 equal 1. And this will be it will be a polynomial calculus, a reasoning of the fact that given Boolean variables, it's not possible that the sum will be equal to 3. Is there any question on polynomial calculus? Okay, so some remarks on polynomial calculus. So polynomial calculus is over the Boolean variables is quite well studied. For instance, we know that polynomial encodings of the pigeonhole principle, random formulas, and some other set of polynomials that are important for proof of complexity, they are hard. They are hard. And for instance, we also have the following structural result that to prove degree lower bounds, it's enough if they are strong enough to prove also size lower bounds. So if you have a degree lower bounds that is omega of n, like n will always be the number of variables. Whenever there is n is the number of variables. So if you have a degree lower bound that is linear in the number of variables, then you have this part will be, and the initial degree is constant. This is the initial degree. This will be about n squared over n, so this is 2 to the omega n. So having a strong degree lower bound will imply a strong size lower bound. And over Fourier variables, this was also studied, but not in so many papers, like in this Beam, Grigoriev, Impagliazzo, and Pitassi, I think, but only for degree. And the point is that for size, the question is much harder. The size is the number of monomials appearing in the proof. And the point is that, one of the points is that this type of theorems in the context of Fourier variables, even plus and minus 1, like the most basic case, this theorem does not hold. So there are counterexamples. And this is one of the class, like the most easy or typical example, like citing formulas or the encoding of citing using polynomials is the following. So you have a graph, and now somehow you want to encode the handshaking lemma. So now you have variables for each edge, and you have an odd number of vertices, and now for each, and now you say that for every vertex, the product of the edges adjacent to that vertex is -1, and the variables are plus and minus 1. So we are in the Fourier encoding. So how to refute this? There is a trivial proof. Just take the product of everything. So the proof is just take the product over all the vertices of the left-hand side. This is the product over all the vertices of -1, which is -1 to the size of the graph. And now, since the size is odd, this is -1. And now each variable is counted twice for the two extremes. So this is each variable is counted twice, and the squares are 1. So this part is 1. So you get 1 is equal to -1, just taking products. And this is something that polynomial calculus is able to do easily, like in a very easy proof, like something along these lines. And so basically, we have short polynomial calculus proofs, but there are degree lower bounds. if the graph is an expander that are linear. So this means that even if you have very strong degree lower bounds, they don't imply very large size, because there is, for instance, this counterexample. And so this means that to get size lower bound, there is some more work to do, and they are not trivial usually. Okay, so right, so this was what I wanted to say about polynomial calculus. But now we want to move to stronger system, like sum of squares and sum of squares over the complex numbers. So let me recall briefly something about sum of squares, the usual one. I guess sums should be written as. But okay, so now we are in the we have again a set of polynomials. Sums of squares can also be used to refute inequalities, but let's focus on the case where we have only equalities. But now the polynomials, they have real coefficients. And now a proof of unsatisfiability is some perhaps quite long algebraic expression of these forms, where you have your initial polynomials, P1, Pm, that are multiplied by some polynomial, again, with real coefficients. And then there are some bunch of squares that are polynomials, again, with real coefficients. And the degree, and then when you expand everything as a sum of monomial, everything cancel out and you get -1. So this will be, so why is this a proof that the original set is unsatisfiable? Because if it was satisfiable with the common solution, all these part will be 0. And whatever that assignment that was satisfying the initial set of polynomial, this part will be something positive, non-negative. And so this, the existence of this algebraic equality will be not possible, because on the left-hand side we get something that is non-negative, and on the right-hand side we get -1. And now, how do we measure degree and size? Of course, it should be before cancellations, because after cancellation is just -1. So before cancellation, the degree is the largest of the degree of these blocks, P1, Q1, Pm, Qm, or the squares, after taking the squares. And the size is the number of monomial in the proof, again, the number of monomial in this part, plus the number of monomial in all these parts, plus the number of monomials in the squares, and so on. And let's take an example, which is Knapsack. So Knapsack is a very simple set of polynomials that are over Boolean variables. And now you say the sum of these variables must be R. And of course, varying where R is, this might be easy or even satisfiable or unsatisfiable, depends. And of course, if R is -1, like in this example, this is not possible, right? The sum of variables that are 0, 1, the sum cannot be -1. And this is a proof in sum of squares of this fact. So you take your knapsack, these polynomials should be this part. Then there are the Boolean axiom, this part, and then some squares. And when you sum everything, you get -1. So this is a proof that the knapsack, when the sum is -1, is unsatisfiable. And right, but there are some results on the hardness of this thing that are the following. So the first one is from Pagliazzo, Pudlak, and Sgal that says, so the knapsack where R, so this R is the how much the variables sum up to, is always hard in polynomial calculus. And hard, I mean large degree and large size. There is a size upper bound of 2 to the n, so this is asymptotically optimal, and there is a degree of upper bound of order of n, so both of these are optimal. And this is also in the weighted version. So even if you put some coefficients here, Ci, this is always hard to refute in polynomial calculus. Of course, if it is satisfiable, it's extremely hard to refute. There are no proofs, there are no refutations. So we suppose like the degree is infinity or the size, something like that, just to not bother if this is satisfiable or unsatisfiable. In sum of squares, the situation is different, because we already saw an example for an R which is easy, and now the breakthrough was this paper by Grigoriev, where he proved that for some R this is hard, And in particular for R that is about n over 2, the number of variables divided by 2. But of course, to not make it trivial should be like not an integer, for instance, like R is about n over 2, but not an integer. So this part will be about 10 omega of n. So this is the degree lower bound that is as large as possible when R is about 10 over 2, but we already saw that when R is -1, this is extremely easy. So at least the sum of squares is able to do something better than polynomial calculus in this context, but still it struggles in some regime, and this is sometimes said like sum of squares cannot reason about integrality or some sentence like that. So, right, so this is about Knapsack, and Knapsack is a crucial example also in our context of the roots of unity, as we will see. But before we go into that, let me put some remarks on sum of squares. So sum of squares over the Boolean variables is a, let's say, somewhat well-studied proof systems. There are a lot of open questions, I think a bit more than polynomial calculus. But we know something. I mean, it is not that we don't know anything. So for instance, we know that polynomial calculus, sum of squares cannot refute unsatisfiable KCNF, but for instance, it can prove the pigeonhole principle easily. Just as a two example of things that we can do. And we also know some structural results, like similar to the one for polynomial calculus that, and this is due to Atserias and Akoniemi, that over Boolean variables, something similar happens as what was happening for polynomial calculus. If you have strong enough degree lower bounds, then they imply strong size lower bounds. So for instance, for Knapsack, if R is about n over 2, this implies the degree lower bound was linear in n, so this is a 2 to the omega of n, size lower bound for Knapsack. And over the Fourier variables, before our work, the only size lower bound known was were proven by in this paper by Sokolov in 2020 over plus and minus 1 variables, where he showed how to construct, how to lift degree d lower bounds for some set of polynomials to exponential size lower bounds, but the caveat is for a different set of polynomials. So there is some gadget involved. And basically, one part of what we prove is like to generalize this technique to generic Fourier variables. And of course, it's a bit more involved. This is something that I could talk in the second part, one of the topics. But there are other things that I could also talk. So, right. So this is something about sum of squares, and basically, to reason about sums of roots of unity, we somehow needed the generalization of sum of squares to work over the complex numbers. And of course, they are not ordered, so there is not a notion of what is positive and so on. So what can we do? We somehow adapted the definition of sum of squares to work over the complex numbers, doing the following. So again, we have a set of polynomial equalities. And of course, in this context, we cannot talk about inequalities. And now the polynomials are over the complex numbers. And now, similar as before, we have some part that is just taking the initial polynomial and multiplying by some other polynomial, now with coefficients over the complex numbers. But there is this part that is somehow the analog of the sum of square part, which is you take a polynomial and you multiply by some formal conjugate of the polynomial. And this notion of formal conjugate might be done in general, but let's do it only in the case of Boolean variables and Fourier variables. So the notion is the following. For Boolean variables, this formal conjugate is just the normal conjugate of S, where you take the same polynomial and you conjugate the coefficient. And over Fourier variables, if the Fourier variables are over Z k equal 1, this S star is the conjugate of the polynomial S after substituting the variable zj with z to the kappa minus j. So the reason to do this is that for whatever assignment of the variables, S star will be always the conjugate. For whatever assignment of the variables, so let's say alpha is an assignment. So the polynomial S alpha and S star alpha will always be conjugate to each other. So when you multiply, this will be some real number that is non-negative. So in this way, we can recover somehow the reason for something that is unsatisfiable, like the soundness of this thing. So if your initial set of polynomials is unsatisfiable, there can, if the initial set of polynomial was satisfiable, there cannot be an expression like this, because as before, if there was some satisfying assignment, this part was zero, and this part will be some sum of modules of complex numbers, so it will be some real number positive. And this should be equal to -1, so this is not possible. And the completeness
this is somehow this is somehow an additional, I mean, you discussed at the beginning arguments for why we want Fourier basis or Boolean basis and not any other one. It's sort of hard to see in general how you could do sums of squares over the complex numbers. I mean, these are somehow the two obvious possibilities.
Yeah. I mean, you could. I mean, as long as you are able to somehow define syntactically what is the conjugate. Somehow, if you have your set of polynomials that are arranging the set of solutions in such a way that you can express the conjugate in a nice polynomial way, then you will be fine. Like so. What is the reason to do this change of variables? Because this z to the kappa minus j is always the conjugate of z to the j, right? The roots of unity, here there is z to the j, here there will be z to the kappa minus j, and they are conjugate to each other. But yeah, in a general context, it will not be possible. It might not be possible, depends. Yes, so basically everything is very similar to before. The notion of degree and size is defined as before. And what else? So the completeness. Why there should be a proof of this? Because already this part. So if you have a set of polynomials that are unsatisfiable by the Null-Stellen, there is a combination of those polynomials that will be equal to 1. So taking them different signs, this would be equal to -1. But in principle, this presence of the squares might help. So this might make proofs much shorter. So this notion of the conjugate might be a bit tricky. So let me make more examples. So suppose that you have this polynomial, which is apart from renaming the variable, is the same as this polynomial. But now, depending on the context, the formal conjugate, and when you take the product, these will be two completely different polynomials, right? If you are over Boolean variables, the conjugate will be just this. You take the conjugate of the I is the imaginary unit. So when you multiply, you get this square, which is sum of squares. It's the module of whatever complex number was there. But if you are over the Fourier variables, then the conjugate of this polynomial will be this one. The real part will be stay the same, the imaginary part will change sign, and then the variables will be flipped in this way. So when you take this product, it might look something weird with complex coefficients, but for whatever assignment you take, this will always, for every assignment that you take that is over the Fourier variables, this will always be the module of a complex number, so it will be always real and non-negative. So, right, and okay, Knapsack again. Of course, now Knapsack, the sum of variables, we could also say something extremely stupid, like the sum of Boolean variables is equal to something non-real. Should be easy to refute, no? Something like that. And the reason it's easy to refute, this is the proof. So basically, Knapsack will be corresponding to this polynomial. The sum of the variable is equal to the imaginary unit. You multiply by this polynomial, you sum a bunch of squares, and this is equal -1. Notice that now we are not using explicitly the polynomial that the variables are Boolean, the xi squared is equal xi, but somehow we are using them implicitly to say that this is a valid expression because these will be recognized as squares. And but here we are again in the Boolean context. Okay, and now the analog of so somehow the reassuring picture is that the hardness of Knapsack, which is somehow the prototypical example, depends on R. It should depend on R, but for real, so when R is real, the hardness is the same as for the usual sum of squares. And when R is not real, then it's always easy. Basically modifying this type of proof. So, right. Another example, like just to get a feeling of what this algebraic system can do, like now we have this type of polynomials. Now we are over the Fourier variables, but let's try to have an intuitive reason why this is unsatisfiable. So I give you a sum of root of unity. I give you a sum of root of unity that is equal -1. And now what are those? Those are the conjugate of the roots. And now you sum the conjugate of the roots and you get 1. But of course, if the sum of the roots was -1, when you sum the conjugate, is just summing the reflection of those roots along the real axis. So it should also be -1. But now here I'm saying that it's 1. So this is trivially not possible for very stupid geometric reasons. And the proof is this one. And again, we are not explicitly using this axiom, but we are using them implicitly to say that this is a valid sum of squares in some sense, because this polynomial is the conjugate of this one. And this polynomial corresponds to this axiom, and this polynomial corresponds to this axiom. Right. So why we want to do this thing over the complex numbers? For instance, for coloring, if we want to use the encoding over the roots of unity, a partial coloring will use numbers that are not real, right? Some of the colors will not be real, and it will be nice to be able to reason about that in sum of squares. So like taking linear transformation, restrictions, partial colorings, or things like that. Okay, so right, some remarks. So this sort of sum of squares over the complex number is a new proof system that is introduced in this work, essentially to have basically the power of the usual sum of squares. And also most of the proofs will adapt to this context because it's just some trivial algebraic extension in some sense. But this will also allow linear transformation with complex coefficients, which is something that we want when we reason about the roots of unity. And some basic property are the following, like at least it's as strong as the polynomial calculus over the same encoding. And if you only care about polynomials with real coefficients and Boolean variables, then you don't care about this sum of squares over the complex, because this is equivalent to sum of squares over the reals.
I actually wanted to ask about this before, but this is just basically, I mean, taking the real part of the whole proof and then you're done, or do you need to do anything more than that?
No, take the real part, yeah. Exactly. No, yeah, exactly. There is nothing. I mean, this theorem, perhaps theorem is overstating, is not that hard. This theorem, the hard part was Berkol's insight on the simulation of polynomial calculus by sum of squares, and basically using similar algebraic qualities, you can do the same in this context. Yeah, I mean, this is just to say how this new system fits compared to the other ones. Okay, so now let's get to the sums of roots of unity. So in some sense, this is an analog of Knapsack, because I mean, algebraically speaking, in some sense. So before you get some part that was Boolean, now there are roots of unity, and you just sum them, and you get some value, some number R that is a complex number. And now the interesting special case is when this sum is 0, like, and hence the title, Vanishing Sums of Roots of Unity. This is an object that algebraist people, they studied starting from Conway and other people, but not from the point of view of the complexity, how hard it is to prove that this is satisfiable or not. So it's not, I mean, even for R equals 0, so when this part is equal 0, this is not, it should not be immediately clear why or when this is satisfiable or not. And the two theorems are the following. So if the roots of unity live in a power of a prime, then this set of polynomials is satisfiable if and only if the prime divides the number of variables. And for the case of a prime, we will see the proof in a moment. If kappa is not a power of a prime, then not power of a prime, then for n large enough, this is always satisfiable. So for us that we want to show unsatisfiability, in some sense, this is not an interesting case, because for n large enough, this is always satisfiable. And this paper by, I don't remember the names, they prove the exact characterization for which n this is satisfiable. But for n large enough is always satisfied.
Is this easy to see, or like it requires some serious thinking?
It's a serious thinking, serious algebraic thinking, yes.
Okay, yeah, thanks.
Yeah, but what doesn't require serious algebraic thinking is this theorem, and this is what I'm going to prove now. So, which is the interesting case for us. So basically, why we want to prove this? Because if we want to show this set of polynomials is hard to prove in sum of squares, somehow we want to know, if we want to get a feeling what would be a human proof of this, right? And if the argument is somehow easy or trivial, then it will say something interesting. If the argument is very complicated, then, well, okay, sum of squares is not able to do it. But if the argument is easy, then the proof will become more interesting. So let's do it for kappa prime. So how to check, so this is mostly an exercise, but let's do it together. So we have this set of polynomial equation, and we want to show that it's satisfiable if and only if kappa divides n. So, okay, assuming satisfiable, so you have some roots, so a solution, which will be some roots of unity, alpha 1 plus alpha n equals 0. And the alpha are roots of unity, kth roots of unity. So now this means that you have some integers, like you have a1 times the first root of unity, plus, let's say 0, plus a1 times the primitive root of unity, plus a2 times zeta squared, plus a kappa minus 1, z to the kappa minus 1 equals 0. And now all these numbers, they are integers, the ai are integers. Right, I'm just saying the root 1 will appear a0 times, the root zeta will appear a1 times, and so on. Well, actually integers, natural numbers, not even in z. Okay, so this means that our primitive root of unity will be the root of this polynomial, a0 plus a1x plus a2x squared plus, oops, start working. Okay. Apple Pencil stopped working. Okay, this is what I was expecting. But well, anyway, I have to fix this. Okay, so the same polynomial. I don't know how to fix this. Sorry. Okay, so basically, okay, zeta is a root of this polynomial, but Zeta is also a root of the polynomial 1 plus x squared and so on equals 0. And this is the minimal polynomial. So when you subtract the multiple of the minimal polynomial to this polynomial, you get a polynomial that has a smaller degree, and since it must be identically 0. So this means that all the coefficients must be 0, and this will imply that A0 is equal to A1 is equal to A kappa minus 1. All of them must be equal. And this means that the number of the, so that means that kappa must divide n, because alpha, all of those will appear the same number of times, all of the roots. Sorry, I don't know why this Apple Pencil died.
So hopefully we'll have time to fix that later. But
yeah.
Sorry, I lost. So you're saying first we're just whatever these integers are. Mm-hmm. You're saying clearly this is like
Okay, so there is a 3x cubed plus a kappa minus 1 x kappa minus 1, right? So zeta is a root of this, but zeta is also a root of 1 plus x squared plus x kappa minus 1.
Just because it's a root of unity.
But the important thing is that this is the minimal polynomial, and here it's when it's used that kappa is a prime. Kappa prime, this is the minimal polynomial. And the minimal polynomial means that z is not a root of a polynomial of smaller degree and integer coefficients. So, but now you can multiply this polynomial times a kappa minus 1, subtract, and subtract. And zeta will also be a root of this new polynomial, and this will be a0 minus a kappa minus 1 plus a1 minus a kappa minus 1 x plus. And now the leading term, this part of higher degree disappears, because I choose to do it exactly for this reason. So the zeta is also a root of this polynomial.
But that can't be, is what you're saying.
But this, the only possibility is that this is identically 0, which means this part must be 0, this part must be 0, all of those must be 0, which means a0 must be equal to a1 equal to a kappa minus 1. So this means that kappa must divide the number of variables.
Very neat.
So the argument is very simple. It's like basically, so showing that sum of squares is not able to prove this satisfiability means somehow sum of squares is not able to reason about divisibility in some sense. And right. Okay, so for polynomial calculus, it's easy to show that this is hard. I will sketch in the second part. It's a simple proof. If the Apple Pencil works, it's a simple proof. Okay, so this I will sketch it quickly in the second part. And now let me tell you the results. So how do they look? So now kappa is a prime, and now you have a primitive root of unity. Now you express your complex numbers using these roots of unity. So R1 and R2 are real numbers, like in the two directions. Instead of using 1 and I, you use 1 and zeta to express all your complex numbers. And now the degree lower bound, you have this condition. So so if you have this, so this is the degree lower bound that you want to prove. Kappa is the number of root of unity. If you have this condition, then sum of squares refutation of this for a generic R requires degree at least D. So a corollary, like the most interesting case, that is R equals 0, so the vanishing root of unity, they require degree at least n over kappa, the number of roots of unity. And this follows immediately setting the parameters in this theorem. And then we're also able to prove a size lower bound. So for simplicity of the statement, let's suppose that n is much larger than kappa. Now, sum of squares refutation of, again, the vanishing root of unity that requires exponential size. And to prove this size lower bound is why we need this more general statement. It's not enough, or at least we were not able to use just the corollary for kappa equals 0, where things are more nice, to prove the size lower bound. We have to move to a more general context and prove when the sum of the unit is equal to some complex number R, the hardness result. Okay. So basically, this is yeah, what you expect. They are difficult both with respect to degree and size. And how you prove it, like a quick sketch of techniques just to get the feeling what you would like to see in the second part, or perhaps not, or just skip it completely. So basically, there are two proved theorems here, right? The degree lower bound and the size lower bound. For the degree lower bound, the technique is similar to what is done for sum of squares over the real. So you want to construct some pseudo expectation to prove a degree lower bound. And the notion of pseudo expectation is just that we use here is just an adaptation of the things for the real. And then there is some extra work needed. And the point is that the simple argument that works for polynomial calculus doesn't work here. But instead, we have to do the following, which is like a proof sketch, like a very sketchy part, just to get a feeling of what you might want to hear in the second part. So we need to go back to Boolean in some sense. We construct a candidate pseudo expectation. There's only one choice under symmetry, so that part might be technically involved, but there is not much reason involved in that. Then interpret this as an evaluation of some symmetric polynomial, use Bleckerman theorem to prove properties of this polynomial, and this would imply that it is a pseudo expectation. Somehow this like roadmap is like standard, but the steps are a bit adapted to this context, and this theorem needs to be generalized to the complex numbers. And already proving this theorem generalized to the complex number, it's might be a different topic, like 2 hours seminar or something. But okay, proving the degree lower bound might be one of the topics that for the second part. And the other is the size lower bound. This is basically a non-trivial adaptation of Sokolov technique to prove size lower bounds over plus and minus 1 variables, but adapted to generic Fourier variables. And basically, the adaptation of the techniques will show the following, that if you have a degree D lower bound for some set of polynomials, then you have a monomial size lower bound. The number of monomial should be, for the polynomial composed by some gadget, should be exponential, but there is some decay that is pretty bad in the number of roots of unity. And the gadget in which you need to compose can be taken as the sum of variables. And since the sums of root unity is something that is just a linear sum of variables, this will play nicely. So when you compose, you get again something related to the sums of root of unity. And that is what allows us to prove the size lower bound for this naturally looking set of polynomial, not for something like strange, like composed by some gadget. And this might be the second the topic for the second part. And let me finish with some open problems. So all the techniques so basically one interesting thing will be to find new techniques to prove size lower bounds in sum of squares, or even polynomial calculus, but size lower bounds for encodings based on non-binomial ideals. So everything breaks down if you start to use encodings like of the form the variables are 0, 1, or 2, or 1, 2, something like that. Anything that is not a binomial ideal will break completely the proof. And of course, and this open problem was the main motivation for us to start this endeavor, was to prove degree and size lower bound, but for the tree coloring, the example that we get at the beginning, or an Erdős-Renyi random graph for the Fourier encoding, so that encoding using the roots of unity. We know some worst case degree lower bound in polynomial calculus by Massimo and Jacob. But for instance, there are no known degree lower bound for the random graph, and even size lower bound, worst case, they are completely open, as far as I know. And another question, which is natural, is like, okay, now you have this system, you use plus or minus one variables. Can you simulate resolution? How? I mean, it's not obvious that you can do it. Even polynomial calculus with plus or minus one variables. How this system relates to resolution. I didn't talk about resolution, but it's a very well-studied and basic proof system. Not algebraic, but it's a very important one. And right, and basically that's it. So right, so this is the more or less the roadmap of what we saw in this talk. And thank you for listening.
Thank you, Ilario. Could you, so I will open up to questions before, so the plan now is to have the opportunity to ask some questions, then we'll have a break, and then the people who wish to hear more can join after the break. But just questions first, if you go back to your open if you want to do this over something like 1, 2, then somehow that means also that probably like you're going to have different categories of variables somehow that evaluate over different domains, or no?
Yeah,
or is it clear?
the issue, yeah. I don't know, perhaps you already gave a shot to prove that.
No, not at all. No.
So one issue is that, so if you are over 1, 2 encoding, now your polynomials are x minus 1, x minus 2, no, for the variable equals 0.
Yeah.
So now when I give you a monomial, now suppose that this is, I don't know, x squared, y squared, z squared, you know, everything is squared. And now you want somehow to reduce the, so you cannot multilinearize basically. And this is because if you multilinearize, then the number of monomial will explode, because x squared, right? X squared is equal x plus 3x. 3x minus 2. So it's a binomial. So when you want to multilinearize this thing, then the number of monomial explodes. So you cannot reason about multilinear things, and this will complicate proofs immensely. Perhaps it's a technical limitation, but I don't see how to overcome this at the moment. I mean, this is, I mean, the encoding 1, 2 is not a very interesting encoding, but going over to non-binomial ideals might involve using new techniques that might be useful in also for polynomial calculus or functional PC, or where you use algebraic expression of higher depth, not just the sums of products, but higher depth. And this is much stronger proof systems than polynomial calculus.
So do you think that SOS over or polynomial calculus over plus minus 1 would polynomially simulate resolution, or you're shooting for a separation?
I tried both directions for a while and both failed equally. I would suspect not, because it would, but I have no idea. I would suspect not.
Did you have candidates for separating?
No, but I remember we were failing with some compositions of orderings or something like that. I mean, having some lifting type of results might seem to help, but the analysis for the So yeah, we want something easy for a solution, right? So perhaps if you lived with an OR, then it's fine. But how to prove that this is hard for sum of squares, we were failing on that. But if you have any idea, let's talk privately or something.
Other questions or comments? So, but I mean, the one obvious candidate is, I guess, the type of formulas that have been used to like relate these algebraic proof systems with and without dual variables. But
yeah, but yeah, but we were not able to do it.